So today we're going to talk about mechanical energy and the mechanical energy balance. So my first question is, how does a siphon work? Can I have a volunteer who thinks they can explain to everyone how a siphon works? And right here we show a siphon taking water out of a bottle.
Because there's a difference in potential energy, there's a difference in pressure. And because of that pressure difference, the water flows from the higher point to the lower point.
Well, the water going from the higher point down to this lower point, that's straightforward, right? That makes sense. It's just falling down. The part of the siphon that makes it work is how it flows from the lower point to the higher point. That's what's unusual. And that comes from the difference in pressure. So just, Connor, if we're thinking of what makes intuitive sense, if I took the pressure right here, and let's say I called it P1, and the pressure up here and called it P2, and we know that the water is running up, is getting pulled up, do you think P2 is smaller or bigger than P1?
P2 is probably smaller than P1 because it's higher than P1. It only has the atmospheric pressure on it.
So we'll talk about that more in a second. You have the right idea. It's lower. And one of the reasons we know it's lower is that if it wasn't, why would the water be flowing up? It has to be sucking it in like you suck in a straw. So you make the pressure lower in order to suck the water up against gravity. Okay, but you have the right idea and you were using all the right words because I also heard you talk about potential energy. So mechanical energy. Again, think back to your physics classes. What is the definition of mechanical energy? Let's get someone else to give us a definition of mechanical energy.
I could try.
Okay, Rankin?
I read it in the textbook just a second ago, but it's like any energy that can be completely and directly converted into mechanical work.
Yes, that is the exact textbook definition. And what that means is that it's useful mostly. So we wouldn't call heat that's just around me in the air, that's energy, but we would not call it mechanical energy because it's hard to make it do anything that we would want it to do. And the forms of mechanical energy that, again, you have talked about a lot in all of your physics classes in your life, or the potential energy that comes from sort of height and gravity pulling down, and kinetic energy, the energy associated with motion. And you should be familiar with these equations. But we're talking about fluids here, and so it's more useful to think of energy per mass rather than this little m here, because if you're talking about a fluid, what mass do you mean? Do you mean the mass of the whole thing, or are we interested at the energy at any point? So it's just more useful to think of it as per mass. Okay. And you know about how kinetic energy and potential energy can transform into one another. So if I have a ball up here and I drop it, it will accelerate as it goes to the ground and as its potential energy turns into kinetic energy. Okay. Now, pressure, which we have been talking about a lot the last couple classes, is not itself a form of energy. We don't really think of it that way, but you can think of it as storing energy. And think of a dam or think of a pressurized tank. So with a dam, how does the dam store energy?
Is that like talking about if you remove the dam, then the water would move?
Yeah, if you remove the dam, the water would move, which there's potential energy there too, because the water is higher on that side, which also means it has more pressure, the hydrostatic pressure we've been talking about. Also, do you remember pressure volume work from physics classes? What would that be? It'd be like a gas usually. So you know that if you have a gas and it expands against pressure, then it's doing work. So you remember pressure volume work, you remember that. That is, and so pressure times volume is units of energy, okay? So pressure times volume is units of energy. So what if I wanted to get the energy stored by pressure per mass? What would that be then?
Would you divide the pressure times the volume?
Yes,
divided
CCA. Divided by what? Sorry?
By density.
By density. Yes, if you divide the pressure by the density, then you would get energy per mass. Okay, because we took PV, divide by mass, pressure by density. All right, so just fix that in your head. Pressure per density is energy per mass.
What happened to the V in that?
Oh, what happened to the V in that is that, so P times V is energy, and I want energy per mass. So divide by mass, that's P times V over mass. V over mass is 1 over density.
Okay.
Okay, good. All right, and so let's take a flowing fluid here, and we're trying to express its mechanical energy. And we could say, we take a combination of the kinetic energy, the potential energy, and the energy stored in the pressure. And this will give us an expression for the mechanical energy of the fluid at any point. Okay, so let's talk about the siphon. Connor talked about the pressure of it being different. So let's look at this, and I'm gonna define 3 points on the siphon. We'll take 1 here, 0.2 here, and 0.3 down here. Okay. Actually, let's do 4 points I want to talk to you about. 0.1, 2, 3, 4. Right? So in between at 0.1, what would our velocity be, do you think?
0.
0. Okay. And whenever we have sort of a big tank, the level is falling, but if it's falling slowly enough, we'll just say the velocity is 0. So that's something to keep in mind. What is the pressure right there?
That would just be atmospheric pressure, right?
Yeah, that would just be atmospheric pressure. And so then down here on 0.4, what's the pressure right there?
Same, atmospheric.
Yep, that's atmospheric pressure. And then the velocity is something we don't know exactly. So what that means is that 0.4 is lower down than 0.1. So we know that somehow through this process, the potential energy at 0.1 has been transformed into kinetic energy down here at 0.4. But in order to do that, we had to get it up over the top. So let's say 0.3 right there. It's going to have some velocity too. Okay. Its potential energy is higher than either 0.1 or 0.2, right? Okay. It's got some velocity, it'll be the same as down there. Okay. So as we're going along the siphon, what happens to the pressure? how about KK? You're kind of in the middle of my screen right now. So could you describe to us what you think happens to the pressure as we go from 0.2 up to 0.3 and down to 0.4?
Okay, so from 2 to 0.3, I would say the pressure decreases linearly, maybe. And then from 3 to 4, the pressure stays the same.
Okay, so you're right that it should decrease as we go from 2 to 3. And why? Because so potential energy is going up. This is going up. If we say the velocity is 0, the velocity is also going up. So from 2 to 3, or you could do it from 1 to 3, either one. That makes sense. So if the kinetic energy and the potential energy both increase and the mechanical energy is constant, what has to happen to the pressure?
It has to go down.
It has to go down. Okay. And then from 3 to 4, then what's happening to the potential energy from 3 to 4?
Decreasing.
It's decreasing. And then the velocity is actually going to stay the same because this tube has the same area. And we talked about how V1A1 equals V2A2. So the kinetic energy has to stay the same. So if the potential energy is going down and the kinetic energy is staying the same, what has to happen to the pressure?
Increase.
It has to increase. So yes, so you were right that from 2 to 3, the pressure will decrease. And then from 3 to 4, it will increase. That means that pressure here has to be less than atmospheric pressure.
Okay, but then wouldn't, I know this wouldn't actually happen, but it kind of seems weird that if you have like a lower pressure here, so the pressure, the low pressure would draw up like the fluid from the other side, but maybe gravity pulls it down more than that lower pressure does, or?
Well, the lower pressure draws up the fluid over there, all right, and then it turns over and then it drops. And remember that you have to prime a siphon. Has anyone ever primed a siphon? You can do this for gas. People have done this. Has anyone ever actually done that? Do you know how you do it?
I have.
Nathan, you've done it. How do you prime a siphon?
So you have to like basically suck up the water to the point where it would start to flow.
Yes, exactly. It won't flow until you put it in your mouth and you suck on it. Like, and the reason you do that is because you have to initially decrease the pressure to get it flowing. And then once you have that, as I said, the low pressure will basically suck it up this way, and then it will dump down the other side just from gravity. All right. And you can do this with the gas, but sometimes you can accidentally get a mouthful of gas if you're trying to siphon a tank this way. Anyway, okay. Point here is the siphon shows us how potential energy and kinetic energy and pressure all balance out.
And then
Yes, Spencer.
just like a quick follow-up on that one. So just to confirm, between points 2 and 3 and 3 and 4, the velocity would be staying the same
Yes.
for all of that, as long as the diameter, or as long as the diameter of the pipe or the tubing stays the same.
Yes.
And our density stays the same, right?
Incompressible fluid, but remember, because we said for an incompressible fluid, V1A1 is equal to V2A2 because of the conservation of mass. So if the diameter there stays the same, the velocity has to stay the same.
Okay, perfect. Just wanted to double check.
Thanks. Yeah, thanks for reminding us all. All right, that depended on an assumption though, is we assumed energy was conserved. Okay. So if total mechanical energy is constant, then just this part equals some constant, which means that constant also equals the mechanical energy at 0.2. And so we can put 2 points in the flow equal to each other. This equation right here, do any of you recognize this? Again, probably physics class is where you would have seen it. Peter, I see.
It looks a lot like the Bernoulli.
Connor, Bernoulli equation. Connor's the Bernoulli equation. I saw some head nods as well. It's the Bernoulli equation. You might also have seen it as like delta P equals blah, blah, blah equals 0. That's the Bernoulli equation. So the Bernoulli equation takes this mechanical energy balance and assumes that the total mechanical energy of our flowing fluid stays the same. Okay. Take a second to write that down. Now, as a reminder here, what are the units of this equation as I've written it here?
Isn't it energy per mass?
Energy per mass, just as a reminder. So this is energy per mass. Energy per mass, but you can also express it in different forms. And so energy per mass right there. You can just multiply everything by density and you get something here where now the units of each term are pressure, or what we call head form, so where everything is units of length. So we're going to use the word head a lot throughout this class. That's what this means. Head means that we express everything in units of length, which means you can take, say, a pressure and divide it by rho g, and you get a head, and that represents a pressure term. All right, so these are all the forms of this. It's helpful to just be able to go between them or put whatever one is most helpful. A lot of you will probably have all of these just sort of memorized by the time we're done because we're going to use this so much.
So all these are still per mass, right?
Yes, the energy form is per mass.
But the other two forms are not?
Nope. This is, or yeah, the other forms are not. This will get you just pressure. So multiply by density. And this one will get you, as I said, units of length. That should make sense, right? Because this says P1 over rho g, and we know P equals rho gh. So we should know that that's units of length. All right. I'm just going to leave this here for a second, but you can go back to the slides and copy all these forms down. I'd like you to be familiar with all of them. So let's do a problem then. Let's find the pressure on the bottom of the tank using the Bernoulli equation. And the first thing we want to do whenever we're doing these mechanical energy balance or Bernoulli equation problems is we want to define a point 1 and a point 2. So we want to find the pressure on the bottom of the tank. So that's going to be one of our points, so I will call that 2, point 2. And now we want to pick another point. This is part of these problems, is knowing which points to pick. We pick one point where we want to know something, and we'll do the other one where we have other information. So the top of this tank, we know that P is equal to P atmosphere there, and we know that the velocity is equal to 0. So we have information there, so that's where I'm going to set point 1. What is Z equal to at the top of the tank, or the surface of the water?
0?
H? Well, it could be. It depends. So do we want to put Z equals 0 at the bottom or at the top?
At the bottom.
Yeah, I'll put it at the bottom. If you're consistent, it's always fine. So if Z equals 0 at the bottom, what is the Z equal to at the surface?
H.
H. Thank you. Okay, and then what is the velocity at the bottom? What's V2?
Zero.
0, yep. And pressure is what we're trying to find. So get me P2 from this.
Do you know how you get rid of this bar at the bottom of the screen? I can't see your letters.
You can't see, there's a bar on the bottom of the screen, you say?
So that bar across the bottom will be visible because of people typing things in the chat window. So what you can do is
Oh.
select the chat window, use your mouse to move it way far over to the side. Just be careful not to make it into a half screen window. And
Alright.
that way the bar will disappear.
Okay, thank you.
Gotcha. Appreciate it.
Okay. All right, so does someone have an expression for P2 from Bernoulli's equation now?
I have P2 equals P atmosphere plus rho GH.
P atmosphere
Or
plus rho
V1.
GH, right? Because you can get that just by solving this. You get this, plug in what we know, P atmosphere plus rho GH. So this is that same pressure at depth equation we've been using and that we talked about last week. I just wanted to show you that you can also get it from a mechanical energy balance. It all works together. But now, so now we have the same situation, but now there's a hole in the bottom of the tank right here. And so it will be draining out. So what I want you to find is the average velocity of water at the bottom of the tank. So go through the same steps that I went through before, define point 1 and point 2. Do this. I'm going to give you about a couple of minutes. We'll see what you come up with. Maybe if you have an answer, put it in the chat.
Do we need to know how big the hole in the tank is?
Okay, no, you do not. Okay, because you're just doing average velocity. You would need to know that if you were trying to find the volumetric flow rate going out. But for the velocity, all you need is mechanical energy. Okay, we've got one answer. Let's wait and see if other people agree. Okay. All right, so we seem to have concurrence, a couple of people still looking down, but let's start thinking about this. In this case, this would be 0.2, 0.1, P1 would be P atmosphere, V1 would be 0, and Z1 would be H, just like before. Now, P2 is equal to P atmosphere. Why do we know that P2 is P atmosphere? KK,
Because
you were
it's,
first, or Spencer. Okay, go on.
I was just going to say, because it's open to the atmosphere, so you would know that P1 and P2 would both be open to the atmosphere, so they're both atmospheric pressure.
Exactly. This is a whole, it's open to the atmosphere, so the pressure there has to be atmospheric pressure. V2 is what we're trying to find, and Z2 is equal to 0. Okay, so these, and then the pressures are equal, so they cancel out too. Oh, sorry, there we go. And so from this, we just get G Z1 is equal to 1/2 V2 squared. Rearranging, we get V2 is equal to square root of 2GZ1, which is square root of 2GH. Okay. Now, we said earlier, remember I said that the Bernoulli equation will be valid is for when total mechanical energy remains constant. Okay. So who can think of a situation, and let's have people answer in the chat again. If you can think of a situation in which a flowing fluid will lose or gain total mechanical energy. So instead of just trading in between these three things, it will be gained or lost. Friction, says Mara. Pumps, if work is done on it, says Rankin, and pumps will do work on this. When heat or reactions are involved, yes. Gas streams that combust, the fluid is radioactive. Yes, that's true too. So whenever there's heat or reactions, whenever there is friction, friction loses energy. Shaft work and friction work, says Avonlea. Avonlea, shaft work. Tell us what shaft work means.
Shaft work usually implies work being done by moving pieces of equipment, so shaft work could apply to the work done by pumps and turbines as well as other things. Okay, yeah. Yes, so shaft work, it's called shaft because if you have a pump, it has this shaft and then it spins around it in order to add energy to the fluid. And then a turbine's the opposite. The turbine has a shaft and the fluid will flow around and turn the turbine. So then energy will be, the fluid will do work on the turbine, so that will take total energy out, which will then go become electricity or something. Okay, so shaft work usually means pumps or turbines. Okay. Rankin says viscosity. So viscosity, the reason, there's always viscosity, every fluid has viscosity. But when viscous forces are significant, they will lead to significant friction. Okay? And so that may have been what you were thinking of. Okay, so where is the Bernoulli equation valid? When we have negligible viscous effects. So I just said that when viscous forces are large, that leads to friction, and therefore, and where are viscous effects significant? Viscous effects are going to be more significant close to a solid surface. Okay. Now you'll get friction, you'll get the fluid sort of dragging on itself with its viscosity. So close to a solid surface like this, then you're going to get large viscous effects and the Bernoulli equation will not be valid. So you want to be at least a little ways. So you want your 0.1
and your 0.2 to be at least a little ways off. How large is large in viscous effects? It depends. We'll see. But in this case, what we mean is large enough that it's comparable in scale to the mechanical energy and potential energy and pressure terms we were talking about before. That's what we mean. Okay. It's also not valid here in sort of a turbulent weight behind an object. Okay. So steady flow. We need steady flow. And steady flow means the velocity at any point does not change with time. So this can be something that's be a little bit confusing because we can have, V1 and V2, and the velocity can change in between V1 and V2, but if you're watching this over time, the velocity at point 1 stays the same and the velocity at point 2 stays the same. That is steady flow or steady state flow. Along a streamline. We have not talked about streamlines yet in class. A streamline basically just means that if we took a little chunk of fluid and we followed it through, it would be a streamline. The significance of this is if you had some sort of closed valve or something that would disrupt it, then you can't do this. So for example, if you had like a valve that was closed, and here's 1 and 2 are before and after it, you can't use the Bernoulli equation between 1 and 2. The closed valve cuts off that streamline and you can't do it anymore. Okay, so we need it for steady flow. What is a situation then that you might encounter in a chemical plant where you would not have steady flow and you wouldn't want to use this?
Batch process.
Yeah, or startup shutdown periods, right? Or a batch process, depending. Negligible viscous effects. So I said close to a surface. And that means that if you have a long, narrow tube, the longer and the narrower it is, the more inaccurate the Bernoulli equation will be. Right? The narrower the tube is, the closer all your fluid inside is going to be to the surface, the more viscous effects, the more friction we'll have. And then the longer it is, the bigger that will be. So just the longer you go on, the more energy will be lost to friction, which we will talk about more later. But so long, narrow tubes. Okay. Wake of downstream objects. So if you have an object, stuff is going on it, you shouldn't do it behind it. In the wake. Sharp entrances. So a sharp edge entrance, like a hole or an exit it goes through, those create significant energy loss. We'll talk about that more later. Partially closed valves, things like that. No shaft work, so not across pumps, turbines, fans. Incompressible flow, which was mentioned before, or someone mentioned incompressible flow in the chat, so that is also true, which that means very big pressure changes, gases with Mach number greater than about 0.3. Again, we will talk about Mach number more in the future. Don't get into it. It doesn't happen that often in your normal life. And heat transfer, so no heating or cooling. And this would also include reactions that are exothermic or endothermic, obviously.
So with this incompressible flow one, what this means is that in 2 points in a fluid, if the fluid is compressed, it can lose or gain energy?
Yep. Yes. In fact, if the density changes significantly, energy will be gained or lost as that happens. Like, because you have to exert some amount of energy in order to compress a fluid. And so it will change that energy. It'll be another term in there.
So that would make sense if you were like pushing the fluid, but what if you had just like a tube that got gradually smaller and you had like really fast? Does that make sense what my question is? Because it kind of seems passive, so it doesn't seem like it would lose energy, but it still does.
Yes, it does. So if it's compressible flow. So a tube that gets gradually smaller, that is another word for a nozzle, right?
Mm-hmm.
And so in incompressible flow, let's talk about this right now. So in incompressible flow, we have 0.1, 0.2. We know that V1, A1 is equal to V2, A2. Okay. So P1 over rho plus 1/2 V1 squared plus GZ1 is equal to P2 over rho plus 1/2 V2 squared plus GZ2. In 0.1 and 0.2, does the height change between 0.1 and 0.2? No, so there's no change in potential energy. And we know that this nozzle had to change the velocity because it narrowed the area, so the velocity got faster. So what has to change in between 0.1 and 0.2?
The pressure?
The pressure.
Or the density, I guess.
The pressure or the density. So in incompressible flow, the pressure. In compressible flow, the density could change too, and it makes the whole thing more complicated, which is why compressible flow nozzles are weird, and we will have a day on them at the end of the semester. Yeah. Okay. Situations when you can't use Bernoulli's equation. And so what? All right, so long narrow tubes, sudden expansions. So let's say you have a pipe and suddenly it gets into a big tank. Energy will be lost there. Again, we will talk about that in depth later. So you can't do that. Fans, heating, wakes, valve like this. This messes up the streamlines, just does stuff. Okay. So we have water draining from a tank again, except this time the water goes through a long hose and comes out here. So now we would point our 0.1 there and our 0.2 there. What do we, if we use the Bernoulli equation, what do we think we'll get for the velocity coming out at the end of the hose?
The same as we got before.
The same as we got before, right? So what did we get before? It was E2 is equal to the square root of 2GH, right? Because the pressure and the velocity and the Z are the same here as they were before, okay? But now we're going to account for the approximation we did. So in order to do that, we had to assume that a negligible amount of energy was lost as it went through this long hole, and that's not a very good assumption, not a very good approximation. So in real life, it does not make sense that the exit velocity would be the same with or without the hose. What assumption made that answer? The answer is the same.
We were assuming that there was absolutely no friction throughout that whole length of the hose.
Yes,
because
we were.
It was long and narrow, there would be some.
Yes. And again, that's not a very good assumption because that hose was the longer and the narrower the hose is, the worse that assumption is. So in reality, as I said, so we made that approximation and we got V2 is equal to square root of 2GH. In real life, how would you expect the real V2 to be different from this approximation? Okay, Seth Tracy says lower. Do people agree? Yeah. Yes, yes. Okay. All right. So, Seth, why do you think the velocity would be lower?
In a real world, there would be friction.
The real world would be friction. And why would that make the velocity lower instead of higher?
Because we would be losing energy.
Because you'd lose energy, right? So you're going to have less kinetic energy coming out the end there than you would otherwise. And with, and so you should be able to account for lots of approximations that way, just sort of with common sense. On Monday, we will be talking about the mechanical energy equation, taking into account pumps and turbines and friction. Right, a concept I want to talk about is stagnation pressure, because this is a term that might come up in your life and I want you to know what it is. So if a fluid is suddenly stopped, so you have a fluid that's flowing along and then it suddenly stops. Okay, so let's say we're going from point 1 here to point 2 there. Suddenly stops. What do you think will happen to the pressure?
Looking at the Bernoulli equation, it looks like it'll have to increase.
It will increase, did you say?
Yes, because the kinetic term drops down to 0.
Yep. Yes, and we can see that from the Bernoulli equation, and we can also just think it through. The kinetic energy term would go to 0, velocity goes away, the height doesn't change, and so if we assume no energy is lost in other ways, the pressure has to rise. Okay, so the kinetic energy term gets transformed into pressure energy. So what is the pressure at the stagnation point? Because that pressure, the stagnation pressure, it turns into, it actually gives us a measure of the kinetic energy inside a flowing fluid. Because we said if all of that kinetic energy turned into pressure, this is the pressure we would get. Okay? And we can do that from the Bernoulli equation. Okay, so we have a point here and some point out there. There's a stagnation point. There's some other point. The height is the same, both of them. The velocity will be 0 at the stagnation point. Okay. So to get the stagnation pressure, it will be this pressure out here, the pressure sort of out in the flow, plus what? And let's get someone from not the first couple pages. I'm just going to call on Brigham Bittner. You there?
Yes, I am.
There. All right. Can you tell me what I need to add to that pressure to get the stagnation pressure?
I am not sure.
Okay, so this P2, we're just going to call that P. We canceled out the Z1 and the Z2 terms. Why did we cancel out Z1 and Z2?
They're equal.
Because they are equal, yes. Okay, I then canceled out this V1 term for right there. Why did I cancel that out?
Your velocity went to 0.
Yes, I hit the front of that thing, the velocity went to 0. And so now I can just solve this equation. Okay, P2 I'm just calling P. P plus what to get the stagnation pressure?
1/2 rho V2 squared.
Yep, 1/2 rho V2 squared. What that means, right, is we can just take the velocity and the pressure of the fluid, and we can say, if it suddenly stopped, this is what the pressure would be.
So what causes stagnation?
It hits the front of this thing and stops, or it has to, the velocity in that direction has to stop right there. Remember when we said that the velocity of a fluid right next to a solid surface is the same as the velocity of that surface? We called that the no-slip effect, or the no-slip condition. This solid surface is at 0 velocity, hits the front, this is running along, it hits the front of it, goes to 0.
So this is inside of a pipe
or anything.
Okay.
Could it also be like pillars of like a bridge in a river, like the one the water hits the front of the pillar, kind of stops?
Yep, it could be that.
That'd be hard to calculate velocity for that, though, right?
Mm-hmm.
Does it stop momentarily and then move to the sides, or?
Yeah, that's what I thought. Yeah, it just go around it because it's water.
Flowing around it like this, but at that exact point, it will be stagnated, it will be 0. But the flow will split and start flowing around the thing. But right there.
So that's only the particles that are immediately touching it?
If we go down to the particle level, I do not know how many particles we would say this takes part in, but right next to it, and right next to it, there's some space that counts as right next to it enough. It'll be velocity equals 0.
Okay.
Okay, you could also get this, so yeah, pillars and a bridge in a river, that would have a stagnation point and a stagnation pressure. They talk about stagnation pressure around airplanes a lot. So you have an airplane and the airplane is flying, it has a very high velocity. When you hit there, the fluid will have technically the same velocity as the airplane, but compared to the airplane, its velocity will be 0. Okay, you have a homework problem like that. Now for our last thing, let's talk about Pitot tubes. This is how a Pitot, I will also tell you that this pressure out here, we call that the static pressure. So that's another word you might see. Okay, this is a Pitot tube. It is a tube like this. It has a hole here, and then it has a hole along the side of the tube. If you look inside of it, the hole in the front goes down to one side of a pressure transducer, and then the hole in the outside goes down to the other side of a pressure transducer, okay? So this pressure transducer will give us the difference between the pressure right here, the stagnation pressure at this hole, and the pressure right there, the static pressure right around it. Why do you think people do this?
Don't planes use that to calculate airspeed?
Yes, they do. Planes do use this to calculate, what did you say, Hunter?
The airspeed?
Airspeed. You do this to calculate airspeed because we just talked about how the stagnation pressure will give us a relationship between P1 and P2 and velocity. And so if you want to measure the velocity at a point, you can use this Pitot tube. Okay.
Wait, so just to clarify, static pressure is the same as stagnant pressure?
No, static pressure is not the same. So static pressure.
So what was the static pressure?
Static pressure is what we call the pressure away from the stagnation point. So the stagnation pressure is the pressure at the stagnation point. The static pressure is the pressure away from it, which would mean in here, P2 would be the static pressure. So this pressure around away from here, that's the static pressure. Someone raised their hand, I saw, and then, okay. All right, 11:50, class is technically over. You can leave if you like, or you can stay and we can work out what the velocity would be for a Pitot tube. Okay, so stay if you want to do that with us.
Can you go back a slide for a second, please?
Yes. All right, does anyone have other questions about this Pitot tube?
So I have a question. Oh, sorry, go ahead.
Do we have to know how it works exactly, or do we just have to know how to figure out the velocity from the stagnation and static pressure?
So here's the thing. That is how it works. If you can use the Bernoulli's equation to figure out how to get velocity from these two pressures, then you already know how the Pitot tube works.
It almost looks as if, so do you need to use multiple Bernoulli's, like do you need to use the Bernoulli equation on the top and then on the bottom?
So what you are getting at is that you do have to make some assumptions to do this, but they're pretty good assumptions. And let's talk about what those are. So let's write out the Bernoulli's equation, right? So I'm going to write out P1 static pressure over rho plus 1/2 V1 squared plus GZ1 is equal to P2 over rho plus 1/2 V2 squared plus GZ2 all right, so P1 and P2, that's P1 is the stagnation pressure, P2 is the static pressure. And you're measuring the difference between them. V1 and V2, which of those velocities will be 0?
V1.
V1. V1 won't be 0. So now we have to make another assumption before we can solve for V2. What assumption would we need to make?
Are we assuming the difference between Z1 and Z2 is negligible?
That is the assumption. We assume the difference between Z1 and Z2 is so small it doesn't matter. It will just be really tiny compared to these other things. Which, if we look at this tube, what is that? That's like a centimeter. It's very small. The difference between there and there. And yes, there are multiple holes around there, and that's just to make sure we have the nice equilibrated pressure.
Dr. Nickerson, I've got a question on one of our assumptions.
Yes, Connor, could you speak up a little bit?
Yeah. So if you go, on this slide, I understand how we can assume that the velocity to be 0, P1, when there isn't a hole. But now that there's a hole, it seems like it'd continue flowing inside. And that's, the point of the device for it to flow inside, meaning the velocity wouldn't be 0.
So that's a pretty small hole. There might be a little bit of velocity, probably not a lot.
Okay.
Gonna hit there. Some of it might keep going down there. So that is another assumption then. Okay. So then we could solve for V2, which is, I'm just gonna call it V because we mean the velocity around here. What do we get?
P1 minus P2.
Okay, P1 minus.
2 P1 minus P2.
Okay, 2 times P1 minus P2. What else?
Divide by rho.
Divide by rho. What else?
And then there's the square root of all of that, right?
Square root of all of that. Okay, and you can see here, something that's nice about this is that all we care about is the difference between P1 and P2. And we don't necessarily need to know what P1 or P2 is. And that is good because it is easy to measure the difference. What this pressure transducer actually does is measures the difference between those two pressures. It doesn't measure each one separately somehow. And so this says we can use this reducer, get a difference in pressure, and turn it into a velocity. And that's how Pitot tubes work. All right, final questions?
Wait, actually, yeah. Okay. Dr. Nickerson, so is the velocity, so V1 is the flow going in through the blue arrow, and then V2 is what it would be coming out of the static pressure holes?
Yeah, so in this case, V1 would be right here. And then V2 would be here, out here. All right.
Okay.
And so we'll just make an assumption that V1 is very, very, very close to 0, which it should be. It's right there at the stagnation point.
But it has to have something in order for the flow to happen through the tube, right?
Oh, flow isn't happening through the tube.
No. Okay.
Through the tube, it's just still, and yeah. Through the
Okay, that's where I was getting confused.
Okay.
So if they're trying to assume that there's no, I just don't really understand how you can have pressure if there's nothing flowing into it.
No. We have 2 days on fluid statics. So when you have a still static fluid, it has a pressure, right?
Yeah, okay.
It does.
Okay.
So, so just to confirm along those lines, so basically these parts of the tube are full of air, and we're just assuming that the part that's open to the front is the same pressure as what's hitting the start.
No, those tubes are not full of air, they're full of whatever that fluid is. So it could be
whatever the fluid is, yeah, but like, so it's open, but like the air hits it, just saying that the pressure is the same.
Yeah.
And then on the outside parts of the point 2, we're saying that the pressure is flowing past it. So that's how you can get the 2 different pressures to give you the equation.
Yes. Okay. And in fact, we can make that assumption because we say the fluid in these long tubes is still, so it will just transfer the pressure of those down to there.
I also remember you saying in the previous slide that the Bernoulli effect, that the Bernoulli becomes less accurate as the tubes become longer and thinner. Is this, what stops this from being the case in this situation? Is it just because it's so short?
Well, also these long, thin tubes, remember there's no flow going through those. And so viscous friction comes from the flow. If it's just still, there's no friction happening, which is why we didn't talk about friction last week when we were talking about static pressure or fluid statics.
Okay, thank you.
Yeah.
So there's no flow going through these tubes.
Yep.
But we didn't assume that V2 was 0. We assumed that there was a velocity in the
V2 will be going this way. Yeah. So V2 will be going this way, sort of horizontal to that circle. Okay. And so we will assume that the pressure right there at the hole is the same. And the velocity is flowing over it. But that doesn't mean that there's velocity inside is the same. Inside it could be 0. And in your homework, you'll be doing a couple of problems that are actually sort of similar to this. You'll do one where there is a high pressure inside and the velocity right next to the wall of a pipe is going to be 0 or close to 0. And then a hole breaks in the pipe. And so you have water flowing through a pipe and then a hole breaks into it. What will happen to the water?
I don't know.
Okay, so you have pressurized water inside a pipe. A hole breaks in it. What do we think will happen to the water?
Water will go everywhere.
Okay, it will come gushing out. So that pressure will turn into a velocity. And I have to get to my next class now. Actually, they're probably already logged on because we use the same link. So if you have further questions, email me or come to my office hours at 2. Also, I did remember to record the class this time. So I will post it and you can watch that. See you guys later.
Thank you.
Okay, thanks.